is your part 2 video for 8.1 integrals as net change. And we're going to pick up here with example 4. So we have a car moving with an initial velocity of 5 miles per hour, accelerates at the rate of a of t is equal to 2.4 t miles per hour per second for 8 seconds. So part A, we want to know how fast the car is going when the 8 seconds are up. And part B, how far did the car travel during those 8 seconds? So for part A, we want to know how fast the car is going. So we're looking at the integral of our acceleration, but acceleration is not constant. So we do have to think about this. You can either think about this as a summation of the acceleration at all the times the rate of change in time, miles per hour. But that doesn't really make sense for this type of question. So what we really want to do here is we want to think of this as an integral. So from 0 to 8 of my acceleration, and then dt. Now, keep in mind, this acceleration from 0 to 8, that is going to tell me my net velocity change. So my net velocity change. However, so it's 2.4 t dt. Remember that we were starting with an initial velocity of 5. So this is all the velocity that I'm adding on to that 5. So once I find my solution for A, I am going to have to add on that 5 in order to figure out how fast we're actually going at the end of those 8 seconds. So if we do antiderivative here, we are going to get 1.2 t squared. We're evaluating that from 0 to 8. So that's 1.2 times 8 squared minus 1.2 times 0 squared. And that's going to be 76.8 miles per hour. So then my total is going to be my initial plus my net velocities. So my initial is 5, my net was 76.8. So at the end of those 8 seconds, the car is going to be traveling 81.8 miles per hour. My total velocity using what we have here, where it says how far did the car travel. So I know that my velocity at any time, using fundamental theorem of calculus, was that initial 5 plus 0 to x of the 2.4 t dt, which whenever we took the integral there, that's going to be 5 plus 1.2 t squared miles per hour. If I want to find the distance that I'm traveling, distance is going to be the integral of velocity. So I'm going to be integrating that 5 plus 1.2 t squared. My bounds are 0 to 8. So that's what I'm going to be using there. Now, typically, you would be looking at the integral of the absolute value of velocity. But because this car is not turning around, it's only traveling in one direction, and that's a positive direction, I don't have to worry because this is never going to be negative from 0 to 8. So we get 5t plus, I have 1.2, I add 1 to the exponent, it makes it a 3, divide the 3 into the 1.2, so it's going to be 0.4 t cubed. And then we're evaluating that from 0 to 8. So again, using fundamental theorem, 5 times 8 plus 0.4 times 8 cubed minus 5 times 0 plus 0.4 times 0 cubed. I did not go down at all. And that's going to be 244.8 miles per hour times seconds. Now, the part B question, it says, how far did the car travel? Well, if I told you it's 244.8 miles per hour times seconds, I have no idea what kind of distance that actually is. So we actually have to go through and do some dimensional analysis to figure out how this is actually going to simplify. So I have 244.8 miles per 1 hour times seconds. So the seconds is going to go on top here. Now, I don't want hours, I don't want seconds, but miles is a distance that I can use. So I want to multiply by some type of equivalent statement to get rid of the seconds and the hours. Well, I know that 1 hour is equal to 3,600 seconds. So that eliminates the hours and the seconds. So I have 244.8 divided by 3,600, which is going to be 0.068, and then miles is my unit. So at the end of the 8 seconds, the car traveled 0.068 miles. So your integral is going to be a natural tool to calculate your net change and accumulation. More than just distance and velocity, though, you can calculate accumulation if you have water leaking out of a pipe, if you have people coming into a store, and if you have people leaving a store, you can actually calculate the different accumulations of what kind of populations that you have. But anytime you want to find a cumulative effect of some type of varying rate of change, you can integrate. It's one of the things that makes this incredibly useful. So for this example, from 1970 to 1980, the rate of potato consumption in some kind of country is the C of T equation. This is in millions of bushels per year, with T being the year since the beginning of 1970. We want to know how many bushels were consumed from the beginning of 1972 to the end of 1973. So if we're looking at since the beginning of 1972, since the beginning of 1970, 1972 would be a time of 2. The end of 1973 is actually going to be a time of 4. Because that would be the beginning of 1974, so that would be from 2 to 4. So if I want to know the total that was consumed, if this is the rate, I'm looking at the integral from 2 to 4 of 2.2 plus 1.1 to the t dt. Now, again, this is not something that you can figure out by hand. The 1.1 causes some issues there, and this whole thing is an exponential. So we would need to pull up our calculator to do this one. So again, I'll just clear out what's there that's still left over from the previous video. So I'm going to do math 9. That brings up my fn int from 2 to 4. My equation, I will need to put a parenthesis in there. 2.2 plus 1.1 to the t power. I don't think I wrote the equation correctly on the previous page. I will go through and fix that if I did not. And then we have the x, and that is going to give us 7.066, and I did not write that correctly. It's correct up in the original problem, I just put that in the wrong spot. So there's to the t. So 7.066 millions of bushels of potatoes. country this is, consumed 7.066 millions of bushels from the beginning of 1972 to the end of 1973. This is an interesting relationship because this is one where we're dealing with people coming into a park and people leaving a park. So it says from noon to 6, the rate at which people enter an amusement park at time t is given by E of t. So that's our graph down here in figure 8.3. T equals 0 corresponds to noon, and t equals 6 is 6 p.m. It says people are also leaving at the rate of this equation. It says if 3,000 people are in the park at noon, so 3,000 people are in there when we're starting this calculation, how many people are in the park at 6 p.m. rounded to the nearest multiple of 100? So we're going to have 2 zeros at the end of our equation. So to figure out how many people are in there, you're going to have your starting amount plus those who enter minus those who leave. So I know my starting amount is 3,000. The amount of people that enter, notice this E of t, that is the rate that people are entering. It doesn't actually tell me that how many people have entered, but I can use this to figure out how many people have entered. And then again, this L of t equation, that's the rate that people are leaving, not how many people have actually left. So my starting is 3,000. The people that enter would be the integral from 0 to 6 of the E of t equation. Now I don't actually have, well, and I say the E of t equation, I don't actually have an equation for this, but using what we learned back in chapter 6, I can find the area underneath this curve, and if I find the area underneath this curve, that would be the same as the integral, because area under the curve is the integral. And then we're subtracting from that the integral of the L of t equation. So we're subtracting from that how many people leave. So let's go back to this picture here. Let's use some geometry. Notice what each box represents. So going up on the y's, that's counting by 100ths. And on the x's, I'm counting by 1s. So I do have this big rectangle. It's a 6 by 400 rectangle. So that is going to be 2,400. And then I have, I can separate this out into, I have a rectangle here, I have a rectangle here, and then I have 2 triangles. So this rectangle that's 2 boxes on top of each other is a 1 by 200. So that's 200. This one is a 2 by 100. So that one is also 200. The triangle on top of this rectangle, it's 1/2 base times height. So half of 2 times 100 is going to give me 100. This one is also, over here on the left, is 1/2 base times height. So half of 3 times 200. So if we do half the 200, that's 100 times 3. So that's going to be 300. And so when you add all those up, 2,400 plus 300 is 2,700. Plus the 200, 2,900, plus the 100, 3,000, and then plus the 200 is 3,200 total. So that's the area underneath the curve. Now, to find the integral of the L of t, you would have to use the calculator for that. So 0 to 6 of 50 times 2 plus t squared e to the negative t over 5, and then that's dt. Scroll here. So 3,000 plus 3,200, oh, not 32,000. 3,200 minus, if you do this on the calculator, you get 2,106 people. I'm not going to show that, but if you do need to see that, please reach out to me and we can work through how to do that on the calculator. But you do need to do a calculator for the LOT. So 3,000 plus 3,200 minus 2,106 is equal to 4,094 people, but it does say rounded to the nearest multiple of 100. So 4,100 people in the park at 6 p.m. It's always a good idea to make a statement that goes back and basically restates what you're trying to find. Like, you don't want to just leave it at 4,100. 4,100 people is a little bit better, but it still doesn't explain the situation. Whereas you could state there's 4,100 people in the park at 6 p.m. So you want to make sure that you do go through and state all of that information. Example 7, I'm actually going to skip this one for the moment. This one is in your textbook. You do have to do a Riemann sum formula, but this one, again, page 390 is where the table is that gives you all this information. So I believe this is covered in your book video, and if not, the example in the textbook does do a very good job of walking through that. So I'm going to hold off on this one for right now. The last thing we're going to look at doesn't appear in the AP exam, but it is a connection for, or an application for the integral. So we have Hooke's law for springs and the fact that work is equal to your force times distance. This does tie into the integral because if you want to know the total work, you have to integrate that force. So you have Hooke's law. Says force it takes to stretch or compress a spring, X units from its natural or unstressed length, is a constant times X. So your force is K times X, K is the force constant, but you do have to integrate that to figure out the total amount of work that's done to stretch your spring. And we're just going to do one quick example on this. So it says it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done to stretching the spring 4 meters from its natural length? So we do need to find the constant first. So that's going to be the force is equal to K times X. So F of 2, which is 10, is going to be that constant times 2. So my constant in this case is 5. So the expression for force is going to be 5x. Well, we want to know the total work that's going to be done. So that is going to be the integral from 0 to 4 of the force used to stretch the spring. So this is going to be the integral from 0 to 4 of the 5x, which is 5/2 x squared, and again evaluating from 0 to 4. So I plug in the 4, I have 5/2 times 4 squared minus 5/2 times 0 squared. That's going to give me 40, and then the units are newtons times meters. So Newton meters is going to be your unit for work. So you can't just do the force times the distance for the work because you want to accumulate the total work. So that's why you need to do the integral from your natural state to how far it was being stretched. Here's your homework assignment for 8.1. This is something that should have already been assigned in Schoology. So just like with everything else, go back, rewatch the first video, watch this video, seek out other places on the internet. Make sure you're utilizing AP Classroom videos as well, and reach out to me if you have any questions.